In this session, we are going to introduce some dimensionality reduction methods. The dimensionality reduction methods, the general concept is in some situations, it could be more effective to construct new space. That means to transform into some reduced number of dimensions instead of using some subspace of the original data. That means the space should be changed. Essentially, originally m times n, you want to get smaller ones. Let's look at this figure. Okay. This figure, if we use the original axis, for example, x and y, you project on x and y, you cannot find nice clusters because all these points actually overlap on both x-axis projection and y-axis projection. However, if we get a new, this dashed axis, okay, this one like turn the y-axis, the axis 45 degrees. What you can see is these points will be projected on these axes to form three nice separatable clusters. That means sometimes we transform a little, but we can reduce the number of dimensions. In the meantime, we can find nice clusters. That simply says, in many cases, feature selection or feature extraction may not focus on finding clustering structures. However, we may use dimensionality reduction method to reduce the dimensionality using some mathematical transformation. There are two very popular approaches, one called non-negative matrix factorization. We will briefly outline the idea in the next slides. The general idea is for one high-dimensional sparse non-negative matrix, we may be able to factorize them approximately into two low-dimension matrices. Okay. Another method called spectral clustering. This we will introduce a little more detail in the next lecture, lecture 10, is to use a spectrum of the similarity matrix of the data to perform dimensionality reduction. So finally, we may find the clusters in a much fewer number of dimensions. This method essentially is to combine feature selection and clustering together. There are two popular spectral clustering methods, one called normalized cuts by Shi and Malik. Another is Ning, Jordan, and Weiss method led by Anju Ying. Published in NIPS 2001, we also call this one NJW method. Let's look at non-negative matrix factorization. Okay. For example, you can think about you get quite a large set of documents, and they have lots of words. Okay. Then the word frequency in documents from a pretty high dimension non-negative matrix. Non-negative because the word frequency can be either a positive value or zero, means there's no such word existing in this document. Okay. So for this non-negative matrix, it could be quite sparse. Then we can do some transformation. That means we can automatically factorize them into the low dimensional non-negative matrices like U and V. Okay. Originally, is n times d is number of words and number of documents. Now you get n times k. K could be much smaller value, and you get another one is k times d. Okay. That means one matrix A with n times d dimensions is factorized into U and V, these two matrix multiplication, where one is n times k, another k by d. Okay. So that means one matrix A is factorized into two factors, U and V. Of course, since it's approximate, that means you may have a residue matrix R represent the noise in the underlying data. This R actually is the difference between the original high dimension non-negative matrix and the factorization, the two factorized matrices, their multiplication, okay, their product. So this transformation essentially is, we can consider it is constrained optimization. That means we can determine U and V as an optimization problem so that the sum of the square of the residues in R is minimized. That means you try to find this R as small as possible. That means this U times B as close as possible. Actually, from the semantic meaning, U and V actually simultaneously provide the clusters on the rows and the columns. Rows, you can think these are the documents. Columns are the words. So this, because you simultaneously clusters on rows and columns, so it's kind of co-clustering. That means for U as a n by k matrix, this essentially are the components of each of this n objects and words is mapped into each of the k newly created dimensions. Okay. Then for V, k times d, you can consider as each of the k newly created dimensions in terms of the original d dimensions. So the advantage is this factorization, get a results, is rather interpretable in the sense because you did not really transform their dimensions. They either represent based on the words or represent based on the documents. Okay, so the data point can be expressed as a non-negative linear combination of the concepts, that means words and documents, in the underlying data. You do not really transform the whole data sets into new axes. So in summary, in this lecture, clustering high-dimensional data, we discussed the challenges of high-dimension data clustering. We also introduced the general methods for clustering high-dimension data. Especially, we focus on subspace clustering methods. We discussed subspace search methods, correlation-based methods, biclustering methods. For biclustering, we discussed delta biclustering algorithm and delta p clustering algorithm. Also, we briefly introduced the dimensionality-reduction methods. For the recommended readings, these are mostly the papers we discussed in this lecture. So you may find a nice original paper you can read. And finally, Arthur Zemek got a nice summary called Clustering High-Dimension Data chapter in Cheryl Agua's book. You may like to read to find some new or additional method we did not discuss in this lecture. Thank you.